Today uh, we will start about a new topic that is Newton-Raphson method. This is also a method for finding roots of non-linear equation. So let us quickly proceed towards a method. Mm, mm, okay, so if we have this say approximate root at x naught of equation, say function fx is equal to 0. And if x1 is equal to x naught plus h be the exact root, then fx1 is equal to 0. So this function f x naught plus h can be expanded in Taylor series terms of Taylor series, and we can neglect the higher order terms here. So h is small, we can neglect the higher power of this h. So basically, this h turns out to be this fx naught and derivative of value of function at x naught and value of the derivative of function at x naught. A closer approximation of root is given by this x1 minus x naught upon fx naught and value of function at value of derivative of function at x naught. So this is known as Newton-Raphson formula. So we will look at it into more detail in our next slide. So this Newton method is useful in cases of large value of f prime x, that is when graph fx while crossing the x-axis is nearly vertical, or if f prime x is small in vicinity of root, then by a h will be large and computation of root will be slow, or it may be not possible. Thus, this method is not suitable for case where graph fx is nearly horizontal while crossing the x-axis. So you can all see here from this graph, if value of function at point A is its corresponding x and y coordinates are x naught and f of x naught, value of function is x naught. So we draw this tangent from that point A. So it will cut this x-axis at approximate point x1. So if x1 is one of the root, is close approximation of the root, then we can write the equation of in straight line as y minus fx naught and f prime, that is slope m, which is given by f prime x naught upon this your um, x minus x naught, and at point x1 we have y is equal to 0, which turns this equation as x1 is equal to x naught minus f of x, value of function at x naught and value of derivative of function at x naught. So this is how we have find our first root, that is x1. Subsequently, we can write this formula in a more general manner. Okay, means we will repeat this process. We will replace this subscript 1 by 2 and subscript 0 not by 1, and subsequently this replacement will lead to find value of x2, that is other root, which is close approximation of the true value. So we will carry out this iteration in this manner and until the sufficient accuracy is reached, and we can write it this expression in more general manner, that is we can see here that it may be written exactly like x it can be written in form of this xi plus 1, that is at ith rotation iteration. What is the value of root xi into value of function at xi point and value of derivative of function at xi point. So this is one another way of deriving this same thing, Newton-Raphson method, analytical method. We can express this function in expand this function in terms of the Taylor series, which is given by equation number 1. And if we neglect the higher power, that is quadratic power, so we are only left with the linear term. And since at the point of intersection, this value of fx will be 0, so we have made this left hand side as 0, and compute the value of xi plus 1, that is, which is one of the approximate root, as xi minus fx1 f prime, and f prime x1. So prime represents the derivative of the function, and fx represent the value of the function at the point. So this is how we compute the root using Newton-Raphson method, using Taylor series method. So some of you people were talking about the convergence rate. Here we will also discuss the convergence rate of this method. So here we can see that mm, aside from derivation, the Taylor series can also use to estimate the error of the formula. So why we are estimating error? If the required error is below the permissible limit, then we will terminate this process, or we'll say that we have reached the required convergence, and that is one of the approximate root of the function. So here we can see that uh, if assume that value of exact root is xr, x suffix r, then we know that this left hand side, that value of that at the point where root is located will be 0. So in this Taylor series expansion, we have made our left hand term as 0, and we have taken up to quadratic term. We can see here that in equation 3 we are expanding this Taylor series up to quadratic term. So next what we do is we subtract equation 2 from equation 3. This is equation number 3, and equation number 2 is something that we went only for the first 2 terms of Taylor series, and in equation 3 we went for expansion up to 3 terms. So if we subtract this equation 3 with equation 2 from equation 3, then we are left with something given by equation number 4. Here we can notice that xr is the one of the real root, yeah, that is true value. So error is given, and xi plus 1 is approximate root. So error is nothing but real value and minus this approximate value. We are getting this error. So I is corresponding to one of the roots. So if we make the substitution, that is, if we replace this xr minus xi plus 1 with corresponding e notation, that is error notation, then we can see here this is nothing but it is equal to this given by equation number 6. So we have we are representing it with this error term, and on rearranging this equation 6, you can see that error is expressed in terms of error in the previous step. So while looking at this equation number 7, we can summarize, make a this statement that according to equation number 7, the error is roughly proportional to square of previous error. So error is roughly proportional to square of the previous error. So if error at the previous step was zero point 0.5, so error is generally means error normally we get in terms of this decimal places only, and if we make it square, then the new error, that is the error obtained in the subsequent iteration, will be square of the previous error. So zero point 0.5, if we square, then it will be much reduced value. This means that the number of correct decimal place approximately doubles with each iteration. That means after every iteration or every calculation, the Newton-Raphson converges much faster, and it is called as quadratic convergence. So we have also discussed this derivation of Newton-Raphson method, and how what is the convergence criteria for this method. On a similar line, you can derive the this calculation for error or rate of convergence for previous two methods which we discussed in on a similar line. So next, since we have discussed these two methods, we will quickly take some of the this numerical problems here. Um, please wait. Some okay.
Sir,
So
is this convergence test only for this method? Means, can we
no,
check the?
no, please pardon your question. I have not.
Sir, I'm asking that here the error which you are checking, like
Yes,
for this method only, it is like, or for rest two also which you taught, we can have like this type of test, like
means
similar.
on a similar this lines, we can derive this the computation of error or computation of error. You can say this convergence criteria for similar previous two methods. Okay. If you are not able to see derive it, then I will derive that also, but that is pretty simpler. And these this computation for the error is never asked in your this exams or any. Only thing is that somebody has asked, that's why we are discussing it, that what is the convergence criteria for this methods, these methods. Okay, so you try it for this bisection method as well as regular false method. Uh, 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 then we'll discuss it if you are not able to get that. But this is also based on this similar lines. Okay.
Okay,
So
sir.
next we will solve some this these numerical problems. Okay, so we are supposed to find the root of a positive root of this equation, that is x raised to the power 4 minus x is equal to 10 up to 3 decimal places using Newton-Raphson method. So Newton-Raphson method, we are interested in finding this roots of this equation. So let us express this equation in terms of a function fx, and we compute the value of this function at 1, that is x is equal to 1, and which we obtain as minus 10, which is a negative value. And similarly we obtain the value of function at point 2, x is equal to 2, and which turns out to be a positive value. So we are sure that the roots will be lying between this 1 and 2. So our next step is to find the more approximate root. So we take x naught as, suppose x naught as 0.2, that is initial value is 2, and we compute the derivative of this function f prime x, which is 4x cube minus 1. So since we have just now seen that we have a general formula for computing the root as per Newton-Raphson formula, which is given here as x n plus 1, that is the root at the which we wish to compute, x n, that is the root at previous step, value of function at minus value of function at previous step, and the value of this derivative of function at previous step. So we see here that x naught is 0, whereas the value of fx2 is turns out to be 4, and f prime 2 comes turns out to be 31, which gives us x1 as 1.871. So this is one of the approximate root. So here also, since we get x1 as 1.871, we will continue this process and we will obtain value of x2, value of function at means next root, which comes out to be 1.856. Similarly, we will calculate this x of 3 value, and we see that f of 3 x3 value is 1.856, which is correct up to 3 decimal places. Okay, so based on this, we see that we have used this formula x n plus 1 is equal to xn minus f value of function at point this xn, and the value of derivative of function at point xn. So we will use this formula and solve more numerical problems. So now over to you people. Please solve next question and give the answer for this question. I have given some of the hint here. Question number 11 is find by Newton method the real root of equation 3x is equal to cos x plus 1 correct to 4 decimal places. So hint is given here is that we can see that root is lying between somewhere between x is equal to 0 and x is equal to 1. So we will proceed our derivation from here itself. So please give the roots using this formula, and the formula which we will use is this xn plus 1 is equal to xn minus value of function at this value of function at xn and value of derivative of function at xn. Okay, only five people have given answer. Ayush, Ankit, Mamta, Ramavtar, and Shivam. Rest, what about the rest of the class? Okay, you tried. We'll see the solution for this question problem. You try the next question on your own, and I expect that more answers will come from you people. So, if you compute this x naught, which turns out to be 0.6, so value of derivative of function is given here. We will use the Newton iteration formula and substitute the value of x naught as 0.6 here and get the value of x1 as 0.6071. This is x1 value. Again, we will use this equation number 1, that is general formula for Newton-Raphson, and substitute x1 as 0.6071, and the corresponding value for x2 we obtained as 0.6071. And here we see that x1 and x2 are equal. We see that Newton-Raphson formula gave the correct answer, one of the root, as 0.671 in the second iteration itself. So now we will proceed towards next problem. So let us see how many of you will give the answer for this problem. So we have a question that using Newton's iterative method, find the real root of x log base 10x is equal to 1.2 to 5 decimal places. So we can express this in terms of function, expression in terms of function, and we compute the value of function at 1 and subsequently at 0.3, which we get as one of the value as negative value and second value as positive value. So root of this fx is equal to 0 lies between 2 and 0.3. So let us take this x naught as 2. Now you proceed to make calculations and give the answer for this question, correct up to 5 decimal places. See this solution for this problem. So here we compute this derivative of this function as which turns out to be this value log base 10x 0.43429, and subsequently using this Newton-Raphson formula we express the this general expression to compute the root of this equation, and on substituting n is equal to 0, which is value of x naught is 2, we get one of the roots of function x1 as 0.281. Since we decide to compute the root to correct up to 5 decimal places, we will proceed from here and see that value of function at x is equal to 4 and value of function at fourth this fourth and fifth iteration is are equal, and from here we conclude that we have reached our desired accuracy and the correct value is 2.74065. So on a similar lines we can move for further problem. So next problem is pretty much straightforward. This is we
सर
have to
स्क्रीन शेयर नहीं
compute
हो रहा है।
सर स्क्रीन विजिबल नहीं है।
अच्छा ठीक. Now you can see this screen.
Yes, sir.
Wait. Okay. So this was the problem which we were discussing. So I will repeat if it was not shared. This is we compute the value of a function at a derivative of this function, which comes out to be log base 10x 0.4342, and we use this derivative to express this root of the function in general term, which is expressed by equation number 1. And if we put the value of n is equal to 0, that is x naught is 2, and get a value of x1 as 2.81. Since we need to calculate the root of this equation correct up to 5 decimal places, so we will proceed our iteration up to fourth and fifth value, and we see that value of x4 and x5 are equal. That means we have reached the desired accuracy, and the correct one of the root of the equation is 2.74065. So on a similar line, we will proceed towards our next problem. This is find by Newton-Raphson method a root of following equation correct up to 3 decimal places. So this is x cube minus 3x plus 1. So you give the answer for this first question, x cube minus 3x plus 1. One of the root of this equation. Okay, so this is one of the root for this first part of this question, 1.532. So this is one of the root for this problem. So you may take this question number 13 as your assignment and solve the roots for the remaining three parts and submit it by next Monday to your class CR. Is question number 13. If you're not able to do this, then we will take same problem in our this after 1 week of time. But first you try it on your own. So these are the four questions. Next, I have the answers for this, but we will discuss once you try it on it your own. So please quickly make calculations for first part of this problem only. Using Newton-Raphson method, find a root of the following equation correct to three decimal places. First part is x raised to x square plus 4 sin x is equal to 0. Okay, so nobody gave the answer for this first part. So the answer for this problem is this 0.853, and so you take these 6 problems as your assignment and previous 4 problems, and you submit it by next Monday. And if you are not able to solve, then we'll take each problem one by one and obtain the solution. But before that, you please try it on your own. These 10 problems and submit it to your class's CR. Okay, so
Sir,
we will wait for you submit it by next Monday. Okay. Okay, we will wait for 5 minutes. Class is over. Those who wish to leave and do not have any query, you may leave. And rest who wish to discuss something, wait for 5 minutes. I will take your queries, and we will end up this class.
Thank you, sir.